Hi. So in this video, we're going to talk about Dantzig-Wolfe decomposition and column generation. All right. So if you remember from the previous video, Dantzig-Wolfe reformulation is suitable for the cases where you have a complicating constraint. So we have this collection of subproblems that I'm encapsulating in this PK. And I have capital K of them. And then my complete subproblem P can be reformulated like so. So basically, this is just that summation that I had in the first row. That's the summation in the second row with my complicating constraint. And this will be the part saying the d1x1 equals d1, d2x2 equals d2, so on and so forth. So the structure that is separable is represented by this. And this is the constraint that prevents me from separating my subproblems and solving them one by one. All right. So, let us have this absurd assumption first that we know every possible extreme point and every possible extreme ray of my subproblems pk. So for each pk, which is formed by that, I know its extreme points and extreme rays. Okay. If that is the case, then I can rewrite this in an implicit way such that I can somehow reobtain this separability, as we'll see in a second. So assuming that I know all the extreme points and extreme rays of that, what I can do is rely on that theorem we saw at the end of lecture 6, that is called the representation theorem, that tells us that any point xk can be represented by a convex combination of its extreme points and a conic combination of its extreme rays. So the conditions for convex combination is that these lambdas are non-negative and sum to 1, and the conditions for the conic combination is just that the thetas, they are non-negative. So Jk is the set of extreme points for subproblem K, and Rk is the subset of extreme rays for subproblem K. So once I start thinking of X like this, I can just go about and represent this, substitute this representation for xk in my problem P. And what I end up with is something that we call the main problem in Dantzig-Wolfe decomposition. You'll see here that this is the original summation K, and this is just replacing. So this used to be summation in K. Let me write a bit more here. The summation in K of C transpose X, CK, XK. So that's what it became. What I basically did was to replace xk with this. And you can see here that I'm considering the extreme points and the extreme rays. A similar effect happens in the constraint. So remember, the constraint was the sum in K of A K xk equals B. So you can see that the elements now get separated again in extreme points and extreme rays. And here I might notice that this problem becomes a problem in lambda and theta now, right? Because these are my decisions. I'm trying to, depending on what I decide in terms of these weights, I'm deciding which of the extreme points I'm getting, or maybe if I'm halfway in between them. Even though we know that when we actually are at optimality, typically it would be at the extreme points of these subsets, but because I have a collection of them and I'm actually the intersection of those, so I'm at an extreme point of the intersection of the subset, which might not be a extreme point of the subset of this all subsets at the same time. And yeah, and I have this constraint, which is a constraint just requiring that I do a convex combination when I talk about extreme points. Okay. So you can see that this formulation is such that I can, this is something that I have only as many as I have rows in B, components in B, or as many as I have rows in AK. And then I have one of these for each subproblem. So if I'm breaking my problem into two subproblems, I have two of those. If I'm breaking in capital K, I have capital K of those. So we can rewrite this subproblem, this main problem PM into a more compact form, which is what we're doing here. So I'm saying that 1 and 2 can be replaced by this combined constraint in matrix form, which is basically telling us, so this upper part here is that original constraint, would be more like so, right? And then I have a lower part involved with these for the convex combination associated with the lambdas. So just for the sake of example, let's say that we have two subproblems, that each subproblem, so jk1 equals jk2, and they only have two extreme points. And just to simplify notation, no extreme rays for now, but you can generalize. Well, let's just say, let's say that we have R1 equals R2 with one extreme ray. So we see it. So that constraint here would look something like so. You have A that multiplies lambda 1, 1 plus I forgot the x1 plus lambda 1 lambda 2 subproblem 2 but lambda, this is gonna become a bit messy. So lambda 2 subproblem 1 x subproblem 1.2 plus a, well, I only have one, so theta subproblem 1 ray 1, and then this is related to k1. Let me put in a different color. This is k equals 1, and then I have here a also multiplying a1 a2 multiplying lambda subproblem 2 node 1 times x2 1 plus lambda 2 2 x2 node 2 plus a2 multiplying theta subproblem 2 ray 1, and that equals b. And that is the part associated with k equals 2. And then I have lambda subproblem 1 node 1 plus lambda subproblem 1 node 2 extreme point equals 1. Lambda 2 1 plus lambda 2 2 equals 1. Okay, so you can see that if you think about this column associated, so if you think about this term associated with, say, x1 1, so this coefficient associated, or even better, the coefficient column associated with the coefficient lambda 1 1 is this x1, our a1 x1, and then I have 1 here, and then 0 everywhere else. See? So the same for this. So for x1 2, I'll have this coefficient, and then I have lambda 2 1 here, so 1 here, and 0 everywhere else. So this column and for W I have this first part, and then 0 everywhere else. Yeah, I wrote theta here. No, yeah, that's correct. It's theta because it's the weight, and W is the actual extreme ray. So here is how we so this is how this is representing really this. So you can see that you have this column of coefficients associated with each of my lambdas, and this column of the coefficients associated with each of my thetas. Being that ek, that vector that has 1 for k for the index k and 0 everywhere else. All right. I hope this kind of helps see what this thing is about. So if you do it like so, then it means that clearly, you know, this primal, this main problem, obviously it's beyond tractability. I mean, why on earth, how would you go about and enumerate every string point and every string ray of your subproblems? This is absolutely wouldn't work. But if you think a bit harder about this, and think about this being the main constraint in the main problem, you can think that once you have a basic feasible solution, the basis matrix associated with a problem PM that has this as a constraint is something that has M, we call it M0, so we differentiate from the number of rows in D. So this is M0. And this I have one per subproblem, so capital K. So this is basically a basis matrix for this problem is M0 plus K times M0 plus K. Okay, and that's the basis, the basis or basic matrix for this. All right. And the other thing you would have to calculate, thinking about trying to solve this with a simplex-like method, would be the dual variables, which you use, you know, to test, to calculate reduced costs and to test for unboundedness, and that thing would be just M0 times K. Of course, it would require BM times -1, which is this size as well. And we needed this vector P, which we use to calculate reduced costs and so on and so forth. And that one is this size. You have one per constraint, and you will have, so M0 coming from here, and then K of those constraints. All right. But again, so structural wise, when we can use a finite and reasonably small structure to represent the problem. I think that the main question comes from this notion of how do you go about having all the columns available, right? And it turns out that if we think a bit more about this, we really don't need, because so let us call this vector P that has M0 plus K, capital K components, be defined by the dual variables like we've seen before, where these are the dual variables with the first M0 constraints coming from the matrix A, and then we have one of these for each of the subproblems, right? Let's say 1 to make things easier, because you have one convexity. You have basically, this is scalars because you have convexity. The convexity constraints are 1 per subproblem, and so you have one dual variable per each of the convexity constraints. So we can then think about, you know, the reduced cost of a given variable lambda, a given variable theta. And once again, the problem is that we can't really enumerate these, so we might have a really incredible large number of these and really incredible large number of those. But when I'm thinking about how to solve this problem in a simplex method-based scheme, I'm only keeping track of M0 plus K, kind of in a revised simplex nature. And the only troublesome part would be when I have to go about and calculate my reduced costs, because then I would have to the full list of available lambda variables and available theta variables to go about and calculate what's the reduced cost of each of those, try to find which is negative, and then, you know, iterate my simplex method like I know very well how to do. But if we look at this closely, look at what's happening here. So this is reasonably possible to calculate because it comes from the matrix B of elements forming the matrix B or its inverse. And the reduced cost is simply, you know, because we're going to be doing, this is the column of my matrix A. This is my vector P. And we know that this is how we get to the reduced cost by doing, you know, our C, by doing Cx. This is the, notice that this is, don't get fooled by this. This is a coefficient. Remember that our problem now, let me go back 2 slides. 2 slides, and notice that our problem is in lambda and theta. So this is the coefficient for lambda, and this is the coefficient for theta. So this is a coefficient. So this is here playing the role of our good old CB, like we've seen before. Okay. So CB minus this term here. So this is the A in the calculation of the reduced cost. Remember that we did reduce the C reduced cost is CB B minus 1A. And this is just the CBB minus 1. Because we know these are the value of the dual variables. So that, and then when we do this product, notice that this is just EK. So I'm basically picking the component that is this small k. So we get that. And this times this, I obtain this term here. So I can put x outside there. All right. And this x was originally there. So this is the case for the variables lambda. And for the case of the variables theta, which are representing extreme rays, I just don't have the minus r here because the component is 0. All right. Now, looking at the reduced cost in this format, that might give you some idea. Because even though I can't list all of those, I can look at the implicit representation of that. And that implicit representation comes from a optimization problem in X. So the key idea here is that I have a finite structure that I can represent my main problem that I'm iterating using this simplex-like approach. So I always have this B or inverse B with finite size. And when it comes then to calculate the reduced costs, which would then be the massive problem because I'll have to do for every single extreme point and therefore have to list them all, what I do is that I use this implicit representation where I just search for a value of X that would return me a reduced problem, a negative reduced cost. Because then it means that I'm looking at an implicit representation of my set P to look for that xk that would have a negative reduced cost, you see. This is that constraint simply saying this here is simply dx equals d. So this is an LP in X. And I have as many of those as I have subproblem K, which is exactly why with this implicit representation, I can recover separability now, because now I can search for those one per subproblem in parallel if you want. So what can happen with this subproblem here is basically two things. This can either be unbounded. So if it is unbounded, it means that this problem is going to be minus infinity. And if it's minus infinity, what you basically found is a direction of P that is unbounded. And if the direction of P is unbounded, it means that the direction is an extreme ray of P. So you just found an extreme ray of P. And we know how to recover extreme ray from an unbounded problem. We saw that in lecture 6 as well. And that means that what I have to do is you just found something satisfying this condition. So it's a direction with negative reduced cost. So what you do, you go and make generate this column, which means that what you do is you're going to get this variable and make it part of the basis. And making this variable part of the basis is basically picking its column, respective column, and getting it to replace whatever variable is going to be leaving the basis in the basis you currently have. So you do whatever rule you have, just selecting the variable leaving the basis, making sure, all those are making sure that you retain feasibility, and this element, this can be your new column. Now, if this is, instead of being unbounded, it turns out it is bounded, so you get a finite value, then two things can happen. You either found a value for the optimal value of this problem, which I probably didn't say, but in the context of Dantzig-Wolfe, this is called the pricing problem. You're looking for a variable with negative reduced costs, and then that's what is called pricing. So if it is so that you found a variable with a reduced cost that is such that it is negative, then it means that this is a variable you're going to be interested in making basic. So you go about and generate its respective column like that, just like the other one. So, get the value of that x you just found, multiplying by a, and then this column makes like so. And that is the non-basic variable, the previously non-basic variable, presumed non-basic variable that you're making basic. So you notice that what is happening is that you know exactly who are your basic variables. So your basic variables are, very well defined, are those that you have a column in the revised simplex method version that you have for this. But your non-basic variables is basically saying, well, is however many extreme points we have minus those that are assumed basic. And of course, also actually including the extreme arrays in the same notion. But you're not exactly listing them explicitly, but only implicitly. And likewise, you're capturing the reduced cost associated with those implicitly with this optimization problem that does the pricing. So yeah, if you found something that is favorable, you add it to the basis. And otherwise, if it is such that, you found a reduced cost that is not satisfying your conditions in terms of all of them positive. So when you minimize all the reduced costs and turns out that they are all positive, then it means that you're finished, you're done, because there is no other variable that will be interested in putting in the basis. It means that that's the optimality condition of your modified revised simplex method. So that is exactly the end of the algorithm. So here is a pseudocode for the Dantzig-Wolfe decomposition as we just described. So you start with a basic feasible solution for your main problem, and we're going to repeat the process of looking at each of the subproblems, solving it, and checking out whether it's unbounded. Because if it is unbounded, then it means that we found an extreme array to consider in our main problem, and for that we need to generate the respective column. If we found out that the value of the subproblem is ck, and we notice that it's less than the value rk. Remember that ck minus rk is our reduced cost. So that means that if this is smaller than this minus this is less or equal than 0. So we just found an extreme point with which is associated a negative reduced cost, meaning that this is a column I want to make basic in my basis for my main problem. So I generate the respective column and make it basic, right? And then once I go around, I'll go and select one of the generated columns to replace the columns in B, and then I'll update B accordingly. And this is the process involving selecting which of the columns I'm going to use and how I'm going to pivot something out of the basis. And I keep iterating this until I observe that all my subproblems are generating positive reduced costs. So that means that there's no variable to generate, no new column to generate, to look into, and then all of them has positive reduced costs. Therefore, I found an optimal solution. So that's just, the algorithm is just that, conceptually very simple, but tricky to implement. Just some remarks that you're gonna need a phase one method to take that into account, the fact you need an initial basic feasible solution for your main problem. So that means having already generated a few columns so you can use them to form your basis. And I think one important point to bear in mind is this, that you're not really generating the columns of every single extreme point and extreme ray, but you only generate them on demand as you keep finding negative reduced costs associated with them. So that's a lot of savings in terms of storage specifically. But clearly, because this is just a variant of the revised simplex method, you shouldn't expect it to have better convergence properties than the revised simplex method itself. The main benefit that is arising from this approach is related to memory requirements. So if you think about the space you are occupying with the structures you're considering is something on the order of the matrix of the main problem plus k subproblems with a space taken by this M2, and this being the number of rows. And this is M1 squared, being M1 the number of rows of your subproblems, because you're solving that small subproblem only with the D's. So this is the space taken by the basis of the subproblems S. And you're doing that instead of having a whole big ass matrix for M0 capital K times M1, because that would be the number of constraints in your problem without the trick of using this notion of implicit representations. So this variant, as I presented you, is what I tend to refer to as Dantzig-Wolfe decomposition. When you think about, when I talk about column generation, I'm usually thinking to this very similar variant, where we are truly working with the notion of delayed column generation, in a sense that at every iteration, we are adding extra variables to the main problem, and therefore creating new columns. So it means that our main problem, it's being repeatedly solved, but while I'm increasing the number of variables in every iteration, which is basically a generalization of what we just seen, but in a context where we would not be using revised simplex method, for example, meaning that, our method is not that specialized, but works in the same principle, where I'm adding variables one per iteration or several per iteration. And this is especially useful in the contexts where you have a problem that you want to solve with something different than simplex method, but you also have the situation where you already have a situation where the number of variables increase exponentially, not because you expecting to list all extreme points and extreme rays, but simply because the way they're generated is grows exponentially. And so pseudocode would be exactly almost the same, if that is possible to say, but it's very, very similar. But I think that the main change here is that if we talk about basic feasible solutions and pivoting a basis, what you have is these lists of extreme points from your original set xk. And then what you're doing is you're solving your main problem in iteration L. Notice that we're using this iteration counter L because the K is taken for subproblems. And then we look at the duals we obtain with our original M constraints, of the M constraints that are complicating, and then one for each subproblem here for the convexification. And then I solve my pricing problem that has exactly the same kind of the same structure. I just using this different notation to denote that this xk is a collection of extreme points in my main problem, while p has that implicit representation with the constraints. So I found a new x from my pricing problem, and if I notice that my reduced cost for that is negative, then I added that new point to my collection of points, and when I'm doing so, I'm creating a new variable lambda to be associated with this new element. Okay, and by doing so, I'm creating something that has the respective column a x bar k, and also the correct multiplier for the convex combination. So you can see that this statement where I'm adding the extra extreme point to this x tilde set is what we mean by column generation. We are physically creating a new variable lambda k to be associated with that element t. Perhaps I could have used L. And that this element is the column associated with that new variable. So if I'm solving a problem with, say, a main problem with, say, 10 variables, then in the next iteration, this is going to have 11 variables, and then 15, 12, 13, 14, and so on and so forth. Or you can add multiple columns as well. So you could have grow, 5 every 5 or every 10, depending on how many you find with promising reduced costs. Of course, you have to manage that, because otherwise your main problem is going to grow too fast. I just removed the unbounded case, but just like we saw before, we could simply add a treatment to capture extreme raise in case our pricing problem is also unbounded. And finally, notice that in either case, column generation, Dantzig-Wolfe decomposition, they are operating on the convexification of your main problem, meaning that you're creating this inner approximation, is going from within towards the intersection of the convex holes of each of the subproblems. This, even though is somewhat hard to see, has the important consequence that the solutions you are obtaining are continuous relaxations, which is not a problem if you only had continuous variables from the get-go. But if some of these variables x were integer, you're going to be in trouble, because whenever you're solving PM, you're getting a continued variable, a continued valued variable. So that was, once that was observed, it became pretty obvious for the optimization community that you could employ a branching mechanism, just like we do in traditional branch and bound, to make sure we obtain from these main problems integer solutions. And that combination of Dantzig-Wolfe decomposition with a branching coordination mechanism to allow for obtaining integer solutions is what we have as branch and price, known as branch and price. So it's a sort of a widely known framework for decomposition that is quite important in several applications where you have exponential number of variables, typically problems that come from the realm of combinatorial optimization problems, right? And that's what is called branch and price. Just to finalize this part, I wanted to bring you this result that is a way for you to keep track of the quality of the solution you have at any given point. So basically, this result is telling us the following. Suppose that we're trying to find this optimal solution value, and Z be the cost associated with the optimal cost of the main problem at the given iteration L. And suppose that we have our RKs, our dual variables, which are associated with those convex combinations. And the ZK, it's the optimal cost of each of the subproblems. So you can see that being the optimal value you're looking for, you can bound for above and from below with information you get in each iteration. So how is it so? Well, this upper part is rather trivial, because remember that um we are looking into the solutions. Let me go back a few steps to this formulation. Recall that we are minimizing, and basically what we are doing is trying to find minimums of ever growing approximations of our feasible region. So basically, the more space, so to say, we are giving, the better we can to search for optimal solutions, the better it is. So the primal, this is giving us, because you have primal, these are extreme points of D, whatever combination of these convex combinations of the extreme points are giving us primal feasible solutions. And because we're minimizing, so the solution of my main problem is going to give them a primal bounds. That's a main difference between the other method we're going to see later, that when you solve the main problem, what you actually get is dual bounds. But in that setting, we're getting primal bounds because they are a combination of feasible solutions. Here we are. Yeah. And then to find a dual bound, we go look into that. So this part comes from just the fact that when you solve PM, that's a primal bound. Now, when we look at the other side, we need to consider the dual of the main problem, which you can see that it can be written like so. If the best way to convince yourself about that is to pause the video here and have a look at how the main problem looks like, and you'll see that it's not really hard to convince yourself that you end up with a formulation that looks like this. And as you might suspect, the reason why I'm looking into this dual formulation is because I want to use a dual optimality, a duality argument, meaning that if we think about a solution of the main problem at any given iteration, I can use an argument of strong duality to show that the value of that z, which is a primal bound, can be written like so, right? With base basically being the the objective function there, with these dual variables there. Now, notice that because we are assuming that these zk's are finite, so they return us a value that we can use to calculate the bound, that means that, when we're solving the pricing problems, the subproblems sk, we are obtaining these values here for them. And of course, these values will satisfy this because there is no extreme raise involved. Otherwise, you'll find a direction where this holds, which is not the case because we're finding finite values. So that means that if you look at this, you can replace zk, or a better said, you can replace rk with zk, and that zk and the variable q, they're gonna form for me a dual feasible solution, because I'm satisfying, it's an R that satisfies this condition if I replace it with zk, and this condition is being satisfied because it's finite. And if you think about that, this is just a dual feasible solution, which is a dual feasible solution for, the actual main problem. So just because it's a dual feasible solution, then it means that I just found the argument to form, I can use weak duality to try to find a bound now for that main value z, the true optimal value z. So I use a weak duality argument saying that, noticing that this is a dual feasible solution. Notice that because it's written like so, this is a dual feasible solution, not only for, it's for P, the main problem, but the main problem considering all extreme points and all extreme rays. So it's a dual, it is truly a dual feasible solution for my original, thinking of the original problem that if I could solve would return me z bar. Okay, so this is why I can use a weak duality argument here using this dual feasible solution, now replacing the r's with z's here. And then I use this old-fashioned trick where I am simply adding and removing this term rk, but rearranging it in a opportune form, because once I rearrange it like so, I can replace this with my strong duality result I have for the current iteration. And that leads us to this substitution. So I can write this as a lower bound for my value. So then the solution at the given iteration for my main problem gives me an upper bound, and with a little bit of algebraic manipulation, I can also calculate a lower bound from the finite value of the subproblems and the dual variables I am obtaining. I've calculated. So for that iteration I am at. So that's it. That's an interesting result, sort of easy to prove, that utilizes our knowledge about Lagrangian duality to give us a stopping condition for our column generation method. Because it's actually quite useful to use bounds instead, because you might be in the situation where you do start to generate variables with very small reduced cost that, even though are negative, they're not really changing that much the objective function at all. You might even be in a situation with multiple solutions where you keep generating, you would be perhaps trying to generate reduced costs which are very, very small. They're supposed to be 0, but for numerical error is not. So this gives you a chance to see whether you are, within bounds, a reasonable bound to stop your method. So that's it for this part. And now in the next video, we're going to look into Bender's decomposition, the other decomposition method I wanted to discuss with you. So see you in the next video. Bye-bye.